Hey, happy Thursday, everybody. So we got a short video for today. Most of the work we've already done this week, working on our stoichiometry problems, and then yesterday working on stoichiometry problems with a limiting reactant. We're still talking about stoichiometry, but we're going to introduce one last part to this. It's the easiest part of stoichiometry, so that's nice. And there's a formula that goes along with it. So for you people that maybe don't enjoy dimensional analysis, this percent yield is going to be a little bit easier for you to do. So percent yield is the topic that we're going to discuss today. And then there are two other types of yields that I'd like to talk about too. When we are doing stoichiometry problems, we're always ending up kind of predicting the future. How much product are we going to have? What mass of product? How many moles of product? We call that our yield. The yield is how much we produce, how much we make. But we can break the yield down into a couple different types of yields. When you are actually doing the math and you're doing these stoichiometry problems, you are solving for the theoretical yield. It's just theoretical. It's just numbers on paper that this is how much we should produce according to the law of conservation of mass. The theoretical yield is not always going to be accurate, though. Sometimes it's better to deal with the experimental yield. The experimental yield is reality. You did the experiment in real life, you measured your product, and this is the mass that you got. That's the experimental yield. It's based on reality. You don't have to do math to figure it out. You can directly measure the experimental yield. So the theoretical yield, it's all on paper. It's what you are predicting that you'll make. The experimental yield, that's what you actually made in reality. So then if we combine these two ideas, the theoretical yield and the experimental yield, we can come up with something that we call the percent yield. And then let's go ahead and look at the formula first. The percent yield is the experimental yield divided by the theoretical yield and then multiplied by 100%. This is just to turn it into a percentage. It's not actually changing the value. So the percent yield, we take experimental divided by theoretical, and then just change it into a percentage by multiplying by 100%. So what this will tell us is how successful our reaction was. Ideally, you're going to get 100% yield. You predicted that you would make this much. That's how much you made. It's 100%. That's not going to happen most of the time. Life is messy. Chemistry can be messy sometimes. You're probably not going to end up with 100% yield. You might have something more like 70% yield or 80% yield for your reaction, and you'd be very happy with that. So why isn't it 100%? And if it's not 100%, doesn't that break the law of conservation of mass? Not really. What could be happening? There's a few things that could be happening. You could have side reactions going on where you are trying to make this one specific product, but along the course of your experiment and your reactions, you end up making some other products, some side products. It's not what you were trying to make, but you ended up making it anyways. That's taking away from your experimental yield. Your theoretical yield says that all that product should be counted as part of the yield. But then in reality, the composition of that product doesn't match what you were trying to make. So you can't count it as the experimental yield. That's how you end up with some lower amounts. Some other reasons are due to human error. Maybe when you were transferring your sample, you spilled some of it. Maybe some of it stuck to the glassware. If you're doing chemistry with really reactive materials, you might have lost some of that matter to the air when it's just reacting with the air or the moisture in the air. There are lots of reasons why your percent yield might not be 100%. And then just real quickly, there are a few reasons that you might get a percent yield over 100% too. If you are measuring your sample when it's too wet, like if it still has a lot of moisture in that sample, you could end up measuring some water just from the environment or from the solution that you were working in. And the water is not really what you want to include in your yield, but it's being measured anyways. So you could end up with an experimental yield that's bigger than your theoretical yield. And that could give you like 120% yield or 130% yield. It just means that your product is not pure. It's not a pure substance that you were hoping for. So you really want to get as close as you can to 100% without being too far under or too far over, because that could mean that your product is impure or that you have lost some of that product along the way. So let's take a look at how we can use this formula here, this percent yield formula. I think I have a slide here. Yeah, Javier. So Javier thought his reaction would produce 50 kilograms of penicillin. Javier is trying to make some medicine, some penicillin here. He did all his stoichiometry, and his theoretical yield is 50 kilograms. He predicted that he would make 50 kilograms. But in reality, it only made 30 kilograms. He actually did this experiment. He made the penicillin, but he only made 30 kilograms. I say only, that's a lot of penicillin. What is his percent yield? Well, we would set it up like this, so that the experimental yield is 30 kilograms. The theoretical yield is 50 kilograms, so we'll divide there and then change it into a percentage just by multiplying that by 100%. Turns out that Javier had a 60% yield here, which is not bad. That's pretty good, at least by my standards. By industry standards, probably not very good. Probably they'd say that's a waste of resources. I personally think 60% is not such a bad yield. So you can see that this percent yield formula is very nice to work with. It's not as in-depth as some of the other stoic that we've been doing. But there are ways that we can tie these two together. Rather than trying to show you on the screen here, I think it'll be a lot easier to do it on the whiteboard wall. Let's just go for 2 examples today. We'll do 2 examples, and then we'll wrap it up so that we can make this video a little bit shorter than the other ones this week. I'm going to close this. We'll get it going on the wall. All right, so let's see if we can apply this idea of percent yield to an actual stoichiometry problem. The reaction that we're looking at here is one that we have actually done in person. We did this in first trimester. It's the zinc sulfide reaction. Very simple, zinc plus sulfur, and then we're going to yield zinc sulfide. The mole bridge, 1 to 1 to 1. Really nice ratios there to work with. My story problem says 4.2 grams of zinc are reacted with excess sulfur, but only 5 grams of zinc sulfide are produced. What is the percent yield? So if I'm following my question word, what is the percent yield? My answer should be a percentage this time. My unit is not going to be grams, it's not going to be moles. My final unit should just be a percentage. So there's that. Another important word here, I see the word excess. We've got excess sulfur. That means we've got more than we need. If we've got more than we need, it is not going to be the limiting reactant. If sulfur is not the limiting reactant, it must be zinc. Zinc is the other one that it gives me information about. I've got 4.2 grams of zinc. And then I know that I made 5 grams of zinc sulfide. I'm going to use that number a little bit later. I'm not quite ready for that yet. So I know that zinc is my limiting reactant. Let's do some stoichiometry based off of that zinc amount to find our theoretical yield. Remember that the theoretical yield is just on paper, how much should we make? That's what I want to find out first. This number here, this 5 grams, that is our experimental yield. That's like we actually went to the fume hood, we did the zinc sulfide reaction, and then we measured our product and we had 5 grams in reality. So that's the experimental yield. Let's solve for the theoretical yield. I'll start with what I know. I know I have 4.2 grams of zinc. I can carry those grams of zinc down. I need to change them into moles of zinc so that I can go over the mole bridge. And then this number here, I'm going to find this from the periodic table. I'm going to look up the atomic mass of zinc. I did this in advance, and it's just about 65.4 grams per mole. I've changed my grams into moles. Now I can go over the mole bridge. Remember, the mole bridge is really easy this time. It's 1 to 1. So 1 mole of zinc will produce 1 mole of zinc sulfide. 1 to 1. It's not actually changing the value at all. It's just letting me change my unit here. And then the final step, I need to change this moles of zinc sulfide into grams of zinc sulfide. This is a molar mass. For the molar masses, I need to use the periodic table. I'll look up zinc, I'll look up sulfur, and I will add those values together. What I'm going to get that time is about 95.9 grams for zinc sulfide. My stoichiometry is set up. I could cancel units if I wanted to. Moles of zinc sulfide, moles of zinc, grams of zinc. The only thing that I have left is grams of zinc sulfide, which is good because that's what I'm looking for this step of the problem. I would go ahead and multiply and divide to solve here. And if I'm using significant figures, theoretically, I should have 6.2 grams of zinc sulfide. That's just on paper. Remember, that's the theoretical yield. I know that my experimental yield is 5 grams. So what I'm going to do, I'll take 5 grams divided by 6.2 grams, and then whatever this answer is, I'll turn it into a percentage. This is how much we actually made. In theory, this is how much we should have made. And then I'm changing it into a percentage. Turns out that this reaction had about an 81% yield. I'd say that's pretty successful, especially for a reaction like this. So what happened to the other 19%? Did we break the law of conservation of mass? No, it's just that some of these reactants reacted with other things. They reacted with other elements and chemicals in the air to make side reactions and side products. We saw this when we did the zinc sulfide lab. We made some toxic gases that were our side products, that sulfur dioxide and the dihydrogen sulfide. So what's happening is that not all of our reactants are making it to this product state. Some of these reactants, some of this zinc and some of this sulfur, are reacting with oxygen and hydrogen in the air, and they're making their own little side products. And that takes away from our total yield at the end. That's why I only ended up with 81% yield for this one. Let's do one more example, then we'll call it for today. All right, one more to end it out today. So, I changed our reaction. We're looking at a different reaction here now. This one's a little bit more complicated with what's going on. We've got lead 2 nitrate. This is like a solution. And sodium iodide. This is another solution. When we mix those two solutions together, we end up making lead 2 iodide. This one is a precipitate. And then sodium nitrite, that one's nitrate, that one's a solution too. It's aqueous. So this is a precipitation reaction. We're making a precip here. This is a solid. Now, if half a mole of sodium iodide is reacted with an abundance of lead 2 nitrate, what is the percent yield considering 150 grams of lead 2 iodide are produced? A lot going on in this problem. It can seem intimidating looking at it all at one part. So let's break it down instead. Let's go with something that's always safe. Let's follow the question word. What is the percent yield? So I want my final answer to be a percentage. I might use grams and moles along the way, but my final answer should be a percentage. I know that 150 grams of lead 2 iodide are produced. This is my experimental yield. I actually did this reaction and I made 150 grams. So that's experimental. I need to come up with the theoretical yield so that I can calculate that percentage. I'm looking for the percent yield. That's what the question says. I know what the experimental yield is. The question tells me. I need to come up with that third part, that theoretical yield. And to do that, I'm going to have to do some stoichiometry. I'm going to start with what I'm given, this 0.5 moles. I included those extra zeros just for significant figures. So 0.5 moles, what's that? Sodium iodide. That's my starting point here. Now, I did make this problem a little bit nice. I started this off with moles instead of grams. Remember that if you start with moles, you can go right over that mole bridge. If you start with grams, you have to do a molar mass first. This is a nicer type. If we're starting with moles, we can go right over the mole bridge. So, I'm going from moles of reactant to moles of product. So check out my units here. My mole bridge is going from moles of product to moles of reactant. This is always how the mole bridge will be. It's getting us over that arrow in the middle of the reaction, from the reactant side to the product side. So what is my mole bridge? 2 moles of sodium iodide for every 1 mole of lead 2 iodide that is produced. My final step here, I need to change those moles into grams. So I made it to moles of lead iodide. I need that in grams so I can figure out the theoretical yield of iodide, lead 2 iodide. Now this last one, this is a molar mass, grams per mole. So I'm going to need to use my periodic table to come up with that number for the molar mass of lead 2 iodide. That's the PbI2. I have this written down here. It is 461 grams, almost exactly, so that works out really nicely. My units cancel out. Moles of sodium iodide, moles of lead iodide. And I only have these grams left, which is what I wanted. I would go ahead and multiply and divide to solve for my theoretical yield. theoretically, this reaction should produce 115 grams of lead-2 iodide. That's my precipitate, my solid. But wait a second. In the experiment, it says that we made 150 grams of lead-2 iodide of that precipitate. So right away, this is seeming fishy to me. Let's go ahead and solve for the percent yield though. Remember that it's experimental on top in the numerator, theoretical in the denominator, and then I just need to convert that into a percentage. So this is unusual. I ended up with an experimental yield that's bigger than my theoretical yield. In theory, I was only supposed to make 115 grams. That was like the max that I could make if it was 100% successful. It looks like I made more than that, 150 grams. If I do the math here, it works out to about 130%. So how's that possible? It's really not. What happened in this problem, this is more of like a human error. What this person probably did is that they measured their precipitate when it was still really wet with solution. So they ended up with an inflated mass, a mass that's bigger than it really should be because it's taken into account all that moisture from the solution that's still on it. So sometimes it is possible to get answers like this, but that kind of reflects that our lab was not carried out very well and that we were not as careful as maybe we should have been. All right, so that quiz is up today. It might be a little bit harder. Like I said, this is the hardest week math-wise. So definitely let me know if you have questions about the quiz or about your grade or about anything, and I can help you with that. All right, I'll see you again next week. Have a good one.